Okay, before we start, can I ask you to mute all your microphones so you can hear me? Okay, thank you very much. Um, so good morning, everyone. I'm sorry for the slight delay in starting our presentation this morning. I apologize for it. I was trying to log in with the Chinese version and had difficulty, but now I'm in. You can hear me. And if you don't, just write in the chat. So today, this morning's program, as I understand it from Yuntech University, is to give you a seminar to the PhD students and graduate students of the Graduate School of Design to talk about the digital turn, what we call the digital turn. And this has been happening over the last maybe 50 years, 60 years, where we look at every aspect of our lives is governed by some degree of digital mediation. And of course, the classic example is the iPhone, right? And or the phone is the ultimate example of that. So today, what I want to do is I want to take you through a very brief history of some of the ideas of this very important period in human history in the field of computational design. So we call it the digital turn. What does this mean? So what I want to do is talk about some ideas for 1 hour, maybe 1 hour, and then open up the session for question and answer. So I will try to speak slowly, and I will try to go, slowly so you can follow. But you are welcome to put your questions into the chat box as we progress. So first of all, I would like to start with me. My name is Professor Shambit Datta, and I am a professor of computational design in the School of Electrical Engineering, Computing and Mathematical Sciences in Curtin University, which is in Australia. I'm trained as an architect. I did my bachelor's and master's in India and Singapore, and then I did my PhD in computational design at the University of Adelaide in Australia. So basically, I work in the area of generative grammars, spatial geometry, urban syntax, and the role of artificial intelligence in design, and have been doing so for the last 25 years. So today, a little bit about my university, just to give you some context with the map of the world. I'm sitting here in this very large state of Western Australia, and we share the same time zone with Taiwan, of course. We are in the same time zone, and we are quite close, actually. You're just directly north of Perth. But we sit on the edge of the west of Australia, and the population of Perth is about 2 million people. This university where I work is a very high research university, and it is also a very large university with almost 60,000 students. It's also a very international university. Almost 30% of our students are international. And so with that, I want to brief introduction. I want to start talking about my talk today. So what I will do is divide my talk into 3 parts, okay? And I want to talk a little bit about this digital turn by comparing these two fields, computation and design. And many of you are designers and computational designers, and you have an understanding of this. But I want to introduce the field and particularly its transformational impact on the theory and practice of design. So I want to cover 3 aspects. I want to cover the theoretical origins of the field and the early applications, not exhaustively, but just to give you an idea of where it all started. And then I want to focus on the second theme, which is thinking, computational thinking, and computational doing through some of my design and research projects, very briefly, that I have been engaged in as well. And finally, I want to discuss computational design as a field of cross-design research and development, because I understand that you are graduate students, you are doing both design in your practice and research, and you're also involved in computation. So let me start by looking at this digital turn in these three aspects. And so here's a diagram that I put up for you in terms of what we are referring to here today. Number one is, of course, thinking, right? And number two is doing, and number three is design. So what does design refer to? Design here refers to creating new computational tools and methods that are adopted by the members of a community to address their concerns. So it's a very broad definition, but it is very clear that it is not design itself, but it's the creation of new tools and methods. And if you want to read a very interesting paper by the computer scientist Peter Denning in 2017, I put it in the bottom here, he wrote a small article on computational design, and it's published in Ubiquity, and the link is also there, ACM Digital Library. You can read about some of these ideas. Now, the first one, computational thinking, is different from computational design because he defines it as a deliberative process that finds a computational solution for a concern. So here is a very theoretical position. Item number one about thinking. Thinking doesn't actually involve, software or tools or methods. It's really a process for finding a solution. So we will investigate this a little bit more in detail. The second one is doing, and this is what most of us do, and that's why it's a big circle. Okay, and that refers to the use of computation and computational tools to address concerns. Now, it's very interesting. You see, I don't talk about any discipline here. I just say concerns because the concerns can be ranging from art to artifacts to pottery to sensor networks to buildings to cities, could be anything. It doesn't matter what that concern is, it's independent. The digital turn of thinking, of doing, and designing applies to all disciplines. So today, of course, we're going to look at some areas that I have worked in, but in your own practice, I'm sure you will be able to apply this to your own area of expertise and work. So I want to take each one of these and I want to start with computational thinking, which is number one. Then I will cover computational doing, which is number two. And then finally, I will talk about computational design, which is number three. So I'll finish with that. So once again, I want you to remember these three definitions, that thinking is a deliberative process that finds a computational solution for a concern. And doing is the use of computation and computational tools to address those concerns. And design is the creation of new tools and methods. So it's a very interesting way of looking at it, which is not normally used. So before I start thinking, before I go into the presentation, I wanted to present this small slide of computational thinking. Okay, and this is from 1966, 1967. Some of you probably not born. I was born in 1966, so 1967, so I was just born then. So in Cambridge University, researchers proposed a kind of computational thinking. They did not use computers. They are just thinking about density, right? how people live in cities and how can we organize them in three different ways. A pavilion, which is the first one. So a pavilion is a building on a plot of land. So the cube here is a building, and the square here is a plot of land. And if you repeat this square and cube like this, very simple, you get a pavilion structure, you get a certain kind of settlement. So they attempted to use the computational thinking to try and address this problem of density. Okay, so here the black is the building, the white square is open space. Then they proposed something called street. Here, the black is a rectangular building and it's still on the same size square. So the plot is the same size as this plot. So when you array this together, the same 4 by 4 squares, you get this kind of building pattern, like a street. Okay? And the third one they call the court. So they use the same size square and they place a cross form building. And then they apply the same square 4 by 4 square to get this kind of building. So here in 1966, 1967, they are not writing computer code, they're doing thinking. So they say, okay, if we have the same square and we repeat that square 4 times by 4 times, if we have a pavilion, we will get this kind of density and structure. If we have a street, we will get this kind of buildings. And if we have a courtyard, court form, we will get this kind of open space in the middle of the buildings. So I wanted to start with this because this is very different from the way in which designers were thinking. Okay, this is becoming now computational thinking. Now, I want to also go into the field of art and look at how computation thinking was affecting art. So this is Lionel March, who is a serial artist, mathematician, and he started to do something in serial art. If you're familiar with art, there was a movement called serialism. And so they try to create shapes which are related. So I'm getting some feedback. Maybe you have to switch off. Thank you. So Lionel March basically used ideas of computational thinking to develop these art pieces. So here, what I see in 1962 is a series of circles. You can see the circles, very easy. And I can see some squares and some blocks, rectangles, very easy. And he put them together in very many different combinations. So for example, here is a point where the circles intersect and the squares intersect. Here is a point where the edge is a tangent to the circle, and so on and so forth. And he created these Palladian linei occulti that he called it. So this was an example of not actually using computers, but computational thinking appearing in art, in architecture, in urban design. Now, interestingly enough, on the other side is what I would call computational doing, if you remember, and computational design, right? So Ivan Sutherland, and you must be very familiar with this name. If not, I strongly suggest you look up this first graphical user interface called Sketchpad. It was a man-machine graphical communication system. And this one was in 1963, and it changed everything for computer-aided design, for interactive design, for graphics, for 3D modeling. And I'm going to play the video from YouTube, if you will bear with me. and I think it's a few minutes long, but it's okay. So basically, I wanted to show you that, but you can watch it on YouTube. You just go and type, Ivan Sutherland Sketchpad, and you'll be able to see it and listen to it. But really, this was a very remarkable achievement in 1963 to have almost every element that we use today, everything that we do in computational design was already in Ivan Sutherland's Sketchpad. So it's important for you to remember that that these ideas are quite old and we are continuously repeating them and improving on them and developing them. So, okay. So I've given you a little bit of a history lesson, I guess, taking you back to the 1960s, but I think it's very important. And now what I want to do is readdress this question that I posed earlier about computational thinking as a deliberative process that finds a solution for a concern. So what do I mean by that? I'm going to use the example of looking at computational thinking and cities, and I would look at, I show you here two different types of cities. One is an ancient city before the car, before automobiles were invented. Cities were very tight, very small. They had irregular network of streets meant for human walking, and most of it was residential and low rise, and that was the technology that we had. So the design became bottom up. Everybody built their houses according to a collective understanding of the rules, and you responded to local context. In the 1920s, this changed because we now had a new invention called the automobile. And because of the automobile, we need to have very straight and long roads. We cannot simply allow the automobile to follow the organic accretive structure of the old city. So we started to design new cities that use the automobile as the generator of the form. So you have highways, you have high-rise buildings, you have open space, and so on. So this was a big change in urban development. Now, if you look at the old city, I'm going to show you an example from my own work in the 90s, almost 30 years ago, which is to look at old cities. And in this case, this is shop houses in Singapore. It is very similar to, say, cities in Taiwan. You have a house and you have a corridor you can walk on, public walkway, 5-foot walkway, and you have a very narrow and long plot. You live on top and you have a shop below. So, this is the ground floor. You can have a staircase going up, and there's a courtyard, maybe a back alleyway, and so on. And that's how it works. So, I wanted to apply computational thinking to understand how this pattern came about because no one really designed it. It came about by some rules. And so I defined some elements of this typology. Shared wall, so every house had a shared wall. A 5-foot walkway, so there was a walkway in which you could go through. There was a staircase, there was an air well, there were courtyards in the front and rear, there were rooms, and there was a service call. So I applied some computational thinking to understand how this organization is happening. Okay, and this is very important to realize that these old buildings in Singapore, perhaps 150 years old, are now being refurbished into very prestigious, very expensive boutiques and highly desirable environments. The same is happening in Taiwan. These ancient buildings are having a new life and having a new way of looking at these old buildings. So I was very motivated to find out, can I look at this computationally and generate in the computer the layouts and variations and plans and possibilities inside Shophouse? When I did this study in Singapore in the 90s, there was a big movement to conserve heritage. They had developed economically and they had many high-rise buildings, but they were also conscious of these small heritage precincts. So it was very topical. So I developed a shape catalog and I gave it a name, a position, size, and then, as Sathilan mentioned, I made instances of these shapes. And then I created labels and entities and transformations, which allowed me to create layouts, two-dimensional layouts based using the digital computer. It was not drawn by hand, but it was generated by rules. So how does this work? So you basically have a rule like this. If you look at this rule, if you have a 000 coordinate, a point, and you create another coordinate at 110, you start there, and then you replace that with a rectangle which has a length and a width, and you give it some labels. If you have this kind of labeling, front, plot, and back, and you have a length, you can add something here. You can subdivide the rectangle. If you have a rectangle, then you can add something at the back, and so on and so forth. So these are basically very simple rules that take a simple shape and say, give it a label and give it some dimensions and say, if some condition is met, you can replace this with another condition. It's what we call an if-then rule. And this was very interesting because what I was able to do is use the computer, an interpreter, to generate different kinds of shapes and different kinds of layouts for the shop houses, but having the same structure. So this is, for example, four different examples with the front courtyard and a 5-foot walkway here, and then two light wells and a back full light well. This one is very similar to that, but it has only a single light well and has half of it is a courtyard, and so on and so forth. So it's a very simple study, but it shows you the power of abstraction in terms of computational thinking. So none of this is drawn, it's all generated. Okay, so that was my first example in the 1990s. And about 20 years later, I started to apply computational thinking again to cities or to forms as a system of recursive rules that create patterns, and you have structure and order and complexity, which you see in non-biological systems. So here is the city of Mali, and it's an island city. It is basically completely built up as a settlement. And I wanted to understand, how did it develop from a simple fishing village to a full-fledged city? And what is its future? And is there a computational way to explain this phenomenon that is happening here in the built environment? So again, I applied some computational thinking. I said that I would look at the whole city as part of the old city, which is an island, and there is some reclamation around it, which is the new city. And I would only look at the street networks, right? And so I divided the city into 6 time slices from 1922, when we had maps, to 2011. And from this, you could generate axial maps, and you have the software which generates maps of streets. And then once you have the network, you can develop which streets are connected to which. We call it node connectivity or network connectivity. So you know the nodes by mathematical means. And once you know the nodes, you can then generate different kinds of mathematical structures which tell you what is the level of the street when it appeared, how important is that street in that network, and so on and so forth. I won't go into the technical details, but the idea here is that you take a concern, which is in this case a city, and you apply computational thinking to address it. So the outcome of that study computationally was to look at 1922, how many streets there were, how many nodes. You had 38 nodes. Node means intersection of two streets, and the 188 nodes, sorry. And then you have some mathematical measurement, which tells you how connected the streets are, every single one, how well this network is functioning. So we use network analysis tools to look at streets in cities, basically. And we look at it in different time periods. And so we can say many different things about the city of Mali in terms of its growth. So, and we have written papers on this, and students have written thesis. So I won't go into great detail, but I wanted to illustrate again how the computational thinking works. The final one that I want to share with you in my work is computational thinking dealing with the spread of architecture in Asia from India. So temple architecture, Hindu and Buddhist temples. And so we all know that, Hindu and Buddhist temples are found in India, in Myanmar, in Thailand, Vietnam, Cambodia, Malaysia, Indonesia, and so on. And there was a lot of exchange of ideas. And historically, we know that they have different types of forms. They are small, they are big, they are huge cities. This is in Yangon in Myanmar, right? A whole 8,000 temples. So I wanted to apply computational thinking to understand how something like a building or an idea of a temple can spread from one part of the world to another part over time. And okay, so basically, I don't want to actually annotate, sorry. I want to just give you a very quick description of this, not go into too much detail. I'm trying to capture here the overall uh, idea of computational thinking. So how do we do this? How do we understand how one idea moves from one part of the world to another over time? So we did many field surveys and archival research, some CAD and photogrammetry and measurements. Then we do some modeling and processing. We develop these kind of flat 2D dissections, and then we put it together into 3D models, and then we make, 3D prints and so on. And so we do it in three phases. So we look at early phase and then how they vary, these old buildings, how they become slightly more typological, and then how they spread and become big, large monuments. So in your PhD work, you will find a similar process, right? Where you have an idea and then you want to find out how to apply computational thinking to this concern of yours. And then you have to map it with a methodology. So here in this sheet, I'm trying to give you a sense of my work and how I map out my methodology. And it always helps to make diagrams and to understand with pictures and also with the output from your processes. So the result of this computational thinking was about 6, 7 years of work with my colleague David Bennon in the University of Tasmania. And we developed 34 case studies, which became a book that we wrote about the spread and adaptation of temples between South Asia and Southeast Asia. So this was also done computationally. And this slide basically illustrates the outcome of our work. So we look here in a map, different periods in different countries. And in the y-axis, you have the timeline. And in the x-axis, you have the different styles of building in different countries. And so we compare them computationally. We develop a comparative model, which I won't go into too much detail, but we can now say, yes, We know how the temples developed in the 4th century, 5th century as these square buildings here, and then, you know, they started to adapt right across Southeast Asia. And this is a sample of temples that, you know, we can describe with computational thinking. So this is not a typical historical study. It's actually part of looking at history by using the digital turn that I described to you earlier. The theoretical basis of this kind of work is very different from normal historical studies. And since you are going to be doing a PhD or you are already doing PhD, it's very important for you to balance uh, the theory with the practice and also your own understanding of where you sit between theory and practice. So I hope this helps you to understand the digital turn a little bit better. So I covered, I covered the thinking part of it. And then I want to go to my second topic today, which is basically doing. And now I'm going to change gears a little bit. And so from the theoretical side, I want to move to more practical problems that computational doing involves, and also explain the digital turn from these examples. So please feel free to ask or write questions in the chat box if you are following, or if I'm going too fast or you're not following. So as I said, my second point is that computational doing refers to the use of computation and computational tools to address concerns. What do I mean by that? So now I'm not taking theoretical position. I'm simply saying I want to solve a problem. I want to do something. I want to create something. And whatever tools I have, I will apply into addressing that problem. So let me show you some examples of this type of work. So this is a very famous building in Melbourne, built in about 20 years ago, maybe 25 years ago, in Australia. And it became very famous because it didn't have a facade. The building is made up of a jumbled set of panels. It's a normal building with this very strange, colorful panels, and it's known as the pixel building. So each panel is like a pixel, and it's actually really very simple shading device. Okay, so each panel is positioned for optimal shading for the glass behind. But the people of Melbourne really loved this building, and of course the architects loved it. And there was a lot of press and excitement about this very colorful building in the middle of the city and these panels. So basically, our question was in computational doing is, this is a great idea. How can we make these panels and simulate these panels so that they are not fixed? If you remember the image I showed you, the panels are fixed, so these cannot change position. They are just stuck and static. So the question we asked is, why should the panels be static? We can make them move because we understand their geometry, we understand their symmetries and tessellations. They're like a tile. So we can put it together as a tile and make them move. And then we can actually rotate the panels. So in this y-axis is each panel having a rotation. And then we can generate some kind of very exciting patterns so that we have a dynamic facade, dynamic envelope. So here it's not a theoretical concern, but we want to achieve something. We want to create a model that can address the problem that we face. So we utilized many different kinds of tools, tessellation and the 2D model 3D tessellation, and then we try to understand the rotation of the tiles. We try to understand how the fixture of the tile would work physically, and we have many different prototypes. So I think a lot of you will be working in this space with prototypes. And the most important thing to realize here is that you don't need to have a theoretical basis for this. You can ask the question, how do I solve this problem? And create a prototype. It can be very simple. It can be very complicated. It can be broken up into a series of prototypes. So then, after many iterations, I'm just showing you the final product. We revisited the pixel building with our own panels. And we said, well, actually, this is a great idea, but the panels now don't need to be fixed. We can move them and rotate them based on many different concepts because we have individual control of the panels. They can close, they can open, they can shade, they can do all kinds of things. So this was a very exciting moment for us because we were able to demonstrate computational doing, which means that we utilize existing tools and existing software, apply computational thinking, and improve a certain kind of artifact or product. In my case, it is usually buildings and cities or heritage. In your case, it can be anything that you're doing, right? So now this also expands our remit from the computer to the 3D printer and the rapid prototyper and the sensor networks, so many different things, okay? So here is the idea of the facade. We are prototyping here with one tile, different model, different geometry, but same concept. Now we want to create this and tessellate it. But we also need to now understand the material properties. We want to be able to design with a certain kind of material, with the computer, of course. And in this case, you can see that there is one tile and its geometry, and then there is 4 tiles, and then we also have examples of 16 tiles, and so that eventually it can become a full facade, right? So this is how the prototyping space works. And I know that in Taiwan, you have very good background and heritage of prototyping in many different fields, from chips, to design. You have, you're very fortunate to have access to great laboratories that can make things. So I strongly suggest that you incorporate some kind of modeling, fabrication, prototyping, very simple process into your thesis activities. It will help you a lot in terms of your computational doing something. Even if it's not theoretical, it's not always about sitting in the library or writing software. Sometimes it's good to make something or solve a very simple problem or extend it by prototyping. So I guess I wanted to give you those 2 examples of computational doing, and I have covered, basically 2 very big areas in very short period of time in 45 minutes. And allow me another 15 minutes to go through the third part, which is the design part of it. So in my definition, computational design, and I've taken it from Peter Denning, refers to creating new computational tools and methods, very important, that are adopted by the members of a community to address their concerns. So when I say computational design, I have to remember, am I creating a new tool? Am I creating a new method? Can the members of my community, do I have a target user community? Can they use it? can they use it to address their concerns? If I can satisfy these three criteria, then I am working in computational design. So it's a much more difficult definition because it involves thinking, it involves doing, but I set a very strict criteria that you must be able to generate a tool and you must, or some kind of method that other people besides yourself can use. So the previous examples I showed you of my experiments cannot be called computational design because nobody else can use them. Only I can use them, right? I can call it computational thinking because it's theoretical. I can write a paper and you can read it. I can say that this is computational doing because I can make a model. But if you want to use it, you cannot. So therefore, I don't classify it as computational design. So let me now talk about computational design a little bit for 10, 15 minutes before we have questions. So this is an example of computational design. Here is a work by Shiwan Wang, who was a student of mine, early student, who then went on to do his PhD in EPFL, and he is now a faculty member in Taipei. He's a Taiwanese student from Tamkang. So he developed this land subdivision prototype because we were given a problem. We want to divide the land, a certain land. If you give the boundary of the land, you want to be able to divide it with some kind of optimizing and criteria. So I'll just play the video here of Shi Wan's work. It's very interesting. And I would say this is computational design because what Shi Wan is doing here is writing a new tool to solve the problem. And I can use it, you can use it, land developer can use it, government can use it, anyone can use it, okay? And what he does is on the left-hand side here, you have a parameters which can be changed. This one is a grid parameter. This one is interaction parameters. And you have these blue and red, green and blue agents. The green agent is basically green space, and the blue agent is built up space. Sorry, there's some feedback. Thank you. And so you can change the grid to whatever you want, right? In terms of the size of the grid, if you are given a plot of land. You can change so many different parameters to suit your requirements. You can make a blue grid, with no green space if you want. And you can also create a network of roads in this blue grid to divide the land. You can also break the geometry if you want. You can create green space just by pushing and pulling some parameters, right? And the system will do the work for you randomly or with some kind of constraints. So we can see here a product of his work and land subdivision. And I would say that this is a very good example of computational design because now it is not Shiwan using it or me using it. Anyone can use it if they have this problem of creating a pattern on a land, which we call land subdivision, right? And so this, I think, should be your goal. Not everyone can achieve this computational design because it involves creating something that other people can use. Very, very difficult, right? But if you can do that, then you have achieved the ultimate goal of computational design, which is, can members of your community utilize your new tools and methods? So this one, as you can see, is limitless, right? You can just go on changing the parameters and it goes on. So I'll just speed it up a little bit. different types of patterns and different kinds of, and it's really about optimization. Underneath this is an optimization engine with agents, and there is no need to understand the technical details behind it because the user interaction and the fact that other people can use it is enough. And it has many different problems. For example, you can see that on the edge of the boundary, it doesn't really work, but that's okay. It's okay not to be perfect. It can still work somewhere, in terms of, you know, um, subdivision, but it's demonstrating ideas and patterns and, thinking around this kind of uh, generation. So I hope that this gives you an idea of what I would call computational design. The next thing is really to look at, maybe that was a computational aspect, but also to look at visualization systems. Human-computer interaction, I would term as very important in computational design, because if your community of users need to use your tool, they need to be able to visualize, have systems, hardware, software, interaction systems, glasses, you know, some kind of toolkit, some kind of software. And so here is our lab at Curtin University, which we call Hive, and we have 4 big displays, very large displays, and we develop uh, visualization systems and human-computer interaction models that allow users, other people, to be able to look at models, galleries, and create virtual exhibitions and interact with these models. So this second aspect of human-computer interaction, I would also call computational design. So allow me to play you this video. Here you can see the big visualization system, and it has the markers and trackers, infrared trackers, a head-mounted display, and stereoscopic glasses. And the user and the community can come and look at the models and interact with these models that we have in this visualization system. So this is a good example of a virtual gallery that other people can use. And I would say that it meets the criteria of computational design because somebody else can use it, somebody else can derive value from it, and so on. Another third one in software is, which many of you may be trying to develop, is developing tools and interfaces, right? So here is one that looks at slicing models in different kinds of models in X, Y, and Z direction. Very simple interface. You have X, Y, Z plane, and you have different layers. And so I can give this model to a school child, for school children, or for history student, or for non-computer literate person to just move the x-axis, y-axis, and z-axis, and they can control the different types of representations, point cloud, in this case point cloud, in the layers which have voxels or 3D models, and they can play with the system within reason. So they don't have to be a 3D modeling expert or a Unity expert or architect to understand this. Anyone can use this tool. The good test is your grandmother can use it to understand something, and that is also, I believe, what I would call computational design. So the development of tools and interfaces and human-computer interaction and data sets is the key area of computational design. So other people can access what you have spent a lot of time and energy and effort doing. Okay, so think about this in your practice, in your own concern. So this is some new work done by a PhD student from India, very exciting work, and also I think is I would call computational design, even though there is no design in it as such, because what he is doing is looking at temple model and segmenting it. In other words, you have a model and you want to divide it differently. So in this case, you can see the three parts of the temple, the base and the walls and the superstructure. In this case, he's looking at the symmetry of the temple. You can see the different types, and the computer can run through this model and find different things in the same model. And so I won't go into the technical detail, but I would say that this is something that other people can use. It's an algorithm, it's a repetitive procedure that can be used to look at models, any kind of model. It could be temples, it could be buildings, it could be, let's say, cars, or any kind of artifact, right? So developing tools such as this, which allow you to look at the same object differently, is also very useful for others and is a part of computational design. The same work here, we are looking at 6 different temples divided into 3 different parts. And we can do classification and comparison of different models by looking at, this is going from the bottom to the top. So we slice it from the bottom to the top. And by looking at comparing consecutive slices, we can kind of create this graph, which is a signature of the change that is happening in the model. Okay, so I won't go again into technical detail, but this is something that other people can use because it's generic. You can compare a geometry or a model, and you can use this to develop new tools and methods that other people can use. So I think that is all I have to present in terms of the theoretical, computational thinking, computational doing, computational design, 3 areas that I wanted to address today. So now I want to move on to kind of summarizing the digital turn, summarizing what is happening with all these tools. In your case, you see 3 things. Enhanced digital exploration. So what does that mean? It means that when you design something, you have options, and these options are increasing exponentially. You can look at this one artifact, you can look at 10, you can look at 10 to the power of 2, 10 to the power of 3, and it'll go on increasing. So we have to find a way to support this enhanced design exploration. Most of your community will want more options, more flexibility. This is very difficult to achieve. So we must keep that in mind when we do our research and our PhDs, that can we enhance the digital exploration? Second one is advanced analytics. People want to know more and more about the quality of the design, from micro to macro, because they're so used to receiving instant analytics from the web, from their phones, from their social media, from every aspect of life. So they want you to present to them the same level of service. Very difficult for us to do. But that's why you're doing the PhDs and specializing, because there will be more requirement for analytics and simulation to improve the quality of design quality. And finally, this is something that you are more familiar than me, perhaps, is the file to factory automation, manufacturing 4.0, robots, file to factory will become the norm. So we will be making things constantly and straight from file to factory. And of course, you have the idea factory in UNTech, and you're already starting to do research to figure out how the future will come to design, when you have to manufacture everything and mass customize. So finally, I want to stop here and say two things in red. Research and industry engagement is key aspect of the work we do in the digital turn, because it's not anymore the universities making innovation. The industry is creating new tools. The industry is wanting and adopting the digital turn, and they need more research. They don't have enough people in research. They can make things, computational doing is very easy for them, right? Computational thinking, not so much. Computational design, not so much. So you have the opportunity to create the research and industry engagement through your thesis, through your research, through your doing. And the rising importance of the research practice nexus. So industry engagement is one thing, where you go to big manufacturing centers, or people who provide you with equipment and hardware and making things. But practice of designers is very important too, because they are the negotiators, and you need to, as a researcher, work with practice, people who are designing things every day, who are making things, and ask them questions. How do you do this? How can you make it happen like this? How can we help? What is the change? Rather than being only with industry, you must also appreciate the importance of practice. So when I say practice, I'm talking about the sort of labs, the co-labs, the co-location labs, the small startups, the small individual designers, small firms, really small and medium enterprises. And when I say industry, I mean the big giants, the Googles and the Apples and the Samsungs and the uh, you know HTCs and so on. So you have to find both these communities in your research and ask how to negotiate and how to manage. You can't do both or not all, but certainly I think these are the two important things from my practice that has helped me understand the digital turn in my discipline. So I'm running basically on time, I guess. I started late. So allow me the liberty of just one last idea, and then I will stop and take questions. So I talked about three things today. I talked about thinking, which is the theory. Very, very, very important. The theory is the key part, but doing, which is the practice, is also very important. And this leads to computational design. So I gave you some examples from my own experience of what maybe thinking, doing, and design. So I want to leave you with this slide because it's a very important one for me in my own personal work. On one side, I show you this picture of a temple taken. This picture was taken 150 years ago when the camera was a new invention, right? At the beginning of photography of this temple that I have studied for many, many years and continue to do so. Now, this photograph is very interesting because this temple is 1,000 years old. And this photograph is 150 years old. Okay, so at the beginning of technology, and you can see it's a kind of sepia black and white picture taken by a famous historian from the United Kingdom who came to India and traveled, and utilized his new camera to take pictures. So this is how the atoms or the material of the world began to be transformed into photographs, originally analog, so the photograph is a representation of the object, And then now the digital turn is flipping this into digital photographs, which you are familiar with. Everyone has, you know, I think that your generation perhaps doesn't appreciate the analog photograph anymore because you have the digital turn already in photography. And then in the temple case, we have the bits, the digital bits. So I have been working with these temples to try and generate models and understand computational thinking, how they designed it, computational doing, how did they build it, and computational design. How can other people utilize these digital representations to further their own concerns? So I think this is a very interesting slide because it takes 1,000 years of history, 150 years of photography, and then maybe 30 years of the digital turn and puts it, to give you a clear idea of how significant this work in computational design and this field that you are in is to the future of so many industries and so many different fields. So with that, I will stop here and hand over to Sherry for questions and interactions. Please ask questions and then we can go through the slides again. If you have any queries or suggestions or questions or comments, I'm happy to answer them now. Thank you very much. You have been very patient with this. So I will stop sharing, or should I keep sharing?
You can stop sharing the screen.
Okay. So how do you stop sharing? Stop sharing. Here we go. All right. Great. So this is my 1 hour rush through the history of computational design, some ideas, and what I want to leave you with is the very basic fundamental ideas that you can utilize in your own work, not necessarily uh, uh, you know, make some very broad claims about the full field. But as a PhD student, as a researcher, as a designer, how do you see your world? Okay. And sometimes you get caught in the detail. So I guess my job today was to bring some kind of perspective of the broad picture. And I hope I have succeeded in doing that. So I will open for Sherry. Thank you, Sherry. I'll hand over to you and mute my